So it's my pleasure to introduce the final speaker of this session, who will be Maarten Stroeks, who is from the Delft University of Technology and is going to be telling us about solving free fermion problems on a quantum computer.
Right, thank you. So indeed, my talk is going to be about solving free fermion problems on a quantum computer. So this is work that is in collaboration with Daan, Lenterman, Barbara Terhal, and Yaroslav Herasymenko. And it's about how a quantum computer can provide a speed up even for a problem that requires, in principle, classically only polynomial effort in the system size. So first, why free or non-interacting fermions? Why is it interesting to solve these problems? So first of all, of course, many systems of interest in physics are and in chemistry are fermionic in nature. Think of electrons or protons. And solving free fermion problems is at the core of computational techniques that solve interacting fermion systems. So it's useful if you can solve these problems as efficiently as possible. And the third reason is that free fermion simulations are also interesting in their own right. Think, for instance, of simulations in quantum transport. These are all essentially free fermion simulations. And then the second question is, why bother solving them on a quantum computer? Because as I said, classically they require resources that scale polynomially in the system size, so polynomially in capital N, where n, speaking of fermions, n will denote the number of modes. But the thing is that this polynomial can become prohibitive for large systems in a very practical sense. So if you want to run large-scale free fermion simulations, you might run into some bottlenecks for interesting system sizes. And so in this work, we try to turn this poly capital N classical effort into a poly log n quantum effort. So our goal is to design an algorithm with end-to-end quantum effort that scales like poly log n. So what are free fermions? A fermionic system in general is defined by these creation and annihilation operators that you might have seen, A and AJ dagger, where J denotes a mode in the system. And these are operators in the 2 to the n dimensional Hilbert space, which satisfy the anti-commutation relations on the slide. And we focus on free fermions in particular. And a free fermion Hamiltonian is an expression that is quadratic in these creation and annihilation operators, in this form over here. And you see that this Hamiltonian itself is like the creation and annihilation operators, an operator on a 2 to the n dimensional Hilbert space. But the nice thing is that these coefficients that are in front of these creation and annihilation operators, these small h jk's, they form a matrix that is Hermitian, and it is only n by n. So that scales with the number of modes in the system. And that will be our object of interest in this work. And we will assume that this small h is an order 1 sparse matrix. So the number of non-zero entries per row of this matrix will be some constant. And a small technical thing that I'll use later is that this leads to the fact that the spectral norm of h is in fact is constant. And many quantities of interest that one would like to determine in practice for these free fermion systems are in fact matrix functions of this small h. And so they are themselves n by n matrices. To give a few examples, so what I'll argue now is that essentially free fermion physics comes down to n by n matrix operations, where n is the number of modes, so much smaller than the many-body Hamiltonian that we were dealing with. And for rho being a quantum state, we define the correlation matrix with these entries. So it's this matrix M, and it's again an n by n Hermitian matrix. So just like small h, it's an n by n matrix. And quantities that we might be interested in learning is, for instance, an entry of the time-evolved correlation matrix. And the interesting thing here is that, as you see on the right, the correlation matrix at some time t can be determined from an initial correlation matrix conjugated by the unitary that implements the time evolution under small h. So this again is an n by n matrix. Now for thermal states, on the right you see the correlation matrix of a thermal state, which has this familiar Fermi-Dirac form. And it's again a matrix function of small h for some beta. And the final object that I would like to mention is the Green's function. Now, it doesn't matter in particular what the shape of this Green's function is, but the point is, again, that it's a matrix function of small h. And so these are all n by n matrices, and they're matrix functions of small h. So you might get the feeling already that, okay, there might be a memory compression coming here. Since we're doing n by n matrix operations, maybe we can represent these matrices using just log n qubits. But an interesting open question then is, can we also get a compression in terms of circuit depth? And that's what we deal with in this work. So our tool to determine our quantities of interest, our observables for these free fermion systems, will be block encoding. And we will block encode the matrices that I had on the previous slide. Let me simply call it A. These are n by n matrices, and we'll block encode it using log capital N qubits into an n plus m qubit unitary. And these block encodings will look as follows. So it's a unitary of which the left upper block equals our matrix of interest A up to some factor alpha, which ensures that indeed UA will always be a unitary. And said differently, the entry I0 and J0 of our unitary matrix will equal the entry Ij of our matrix A up to some constant alpha. And in order to block encode the matrix functions of interest that I had on the previous slide, we will use an existing technique for block encoding polynomials of a sparse matrix by first polynomially approximating the matrix functions of interest and then directly block encoding those polynomials. And just to mention here that our tool here is the block encoding, and there's a related work, independent, very nice work by Google, where they have an alternative encoding into the entries of a so-called shadow state. Okay, so let me get to the overview of the algorithm. Let me start at the end here. So our goal is to estimate an entry of A, which could be the thermal correlation matrix or the Green's function or whatever. And in order to estimate these entries, we will block encode A. And in order to block encode A, there's two components that we need. The first one is a block encoding of small h, this sparse single body Hamiltonian if you want. And in order to realize that block encoding, we simply have to realize sparse access to h, and then we can use existing techniques to realize the block encoding of small h. And the second component that we will need is a description of A in terms of h. And this will come in the form of these polynomial approximations that I mentioned. So let's get into the first building block, which is the sparse access to h. So h is a matrix that has constant sparsity, but the total number of non-zero entries of this h might still scale with capital N. So if we want to realize our polylog n quantum algorithm, then we have to input h in a different way. And the way this can be done is through realizing sparse access to h. And this sparse access comes down to two oracles. The first one is oracle OR, and the second one is oracle OH. So these are the row oracle and the matrix entry oracle. And the row oracle gives, for a given input index I, gives the locations or the column indices of the non-zero entries of h in that row. And the matrix entry oracle gives, for a given set of indices I and j, the actual entry of h at location ij, or at least an approximation of it. And if we can realize these two oracles, then we can realize a block encoding of h using existing techniques, because we will only need a constant number of calls to these oracles. But as I said, we want our algorithm to have polylog n total effort. And so we need to ensure that these OR and OH oracles are actually implementable as unitaries of polylog n size. And for many applications, this can be done by simply employing circuits that perform modular arithmetic. So example applications for which this can be done are, for instance, d-dimensional lattice models or some expander graphs. We also work this out for disordered models, and a recent paper by Chen from Caltech works this case for disordered models out in a lot more detail. Okay, so I've talked about the sparse access to h using these oracles OR and OH. that allows us to do a block encoding of H. Now let's get to the second component that we need, which is a description of A in terms of H. As I said, we will input this information using polynomial approximations, and an important point here is that using existing techniques, we know that the depth of a block encoding of a polynomial of degree d will scale linearly in d. So as long as we can take d to be polylog n, and that gives a sufficiently accurate polynomial approximation, we're in business. So let's consider block encoding the thermal correlation matrix, or getting a polynomial approximation for it. If we want to do that, we need to polynomially approximate this function over here. And the tricky thing is that this function has poles on the imaginary axis at I pi over beta, 3 I pi over beta, etc. And so if beta scales with system size, we know that a Taylor expansion, for instance, will have a region in which it's valid that will go down with beta. So ideally, we will have a method that gives a good polynomial approximation on some constant range along the real axis, because our small h will have a spectral norm that is also constant. And the method that allows us to do this is by using Bernstein's theorem. And what Bernstein's theorem says is that if we draw an ellipse of this shape, which includes the points -1 and +1 along the real axis, then if the function that we're trying to approximate is bounded sufficiently strongly on this ellipse, then we can get a high quality polynomial approximation on the interval -1 to +1. And in particular, for this specific application of the thermal correlation matrix, we get an error that scales like beta to the 4th over d. And since we have set ourselves the limitation of d being polylog n, we see that for beta as polylog n, we are in fact in business. And similar methods can be used to polynomially approximate the Green's function, and other methods for polynomial approximations can be used for the problem of time evolution. Okay, so now we've dealt with the two components that allow us to block encode A, and the thing that's left to do is to actually estimate entries of A. And this can be done using pretty straightforward methods, pretty standard methods, because the entries of our matrix functions of interest correspond to correlations or entries of the Green's function, which is what we want to learn. And using standard routines like the Hadamard test or quantum amplitude estimation, we can obtain these entries with effort only scaling like 1 over epsilon squared or 1 over epsilon, so that's good. And another thing is that we can use these methods to also estimate, for instance, global observables like the energy density or the particle number density, by combining our ability to estimate entries of the correlation matrix with some sampling techniques. Okay, so we've dealt with our algorithm. That's all fine. We can estimate these entries with total polylog n effort. But now the question is, how hard are these problems, right? How hard are these free fermion problems? Well, at least for the time evolution problem, we know it's BQP hard. And the way to see this is that if we want to determine a diagonal entry of the time evolved correlation matrix, which would correspond to, for instance, the occupation of some mode J, and we want to say at time t is polylog n, is this occupation at least 1 over polylog n, or at most 1 over poly n, then we know that this problem should be BQP hard, because if we would take the initial correlation matrix to be a very simple one, namely mode 1 is occupied and the rest is empty, then we know that this problem maps onto this general Hamiltonian dynamics problem, so it's BQP hard. And then BQP completeness follows from our algorithms. But what about the complexity in specific settings? We want to apply it to physically interesting models, so what can we say about the complexity there? Let's focus on lattice models for now. So lattice models are in fact easy classically, in the sense that if we limit ourselves to the parameter regimes that we can reach using a quantum algorithm, then for lattice models we can do the same things classically. So let's focus again on our example of estimating an entry of the thermal correlation matrix. So we have constructed a polynomial approximation with an error that scales like beta to the 4th over k, where k is the degree of the polynomial. And we've said that for a quantum algorithm, we take beta as polylog n. And in addition, we need classical sparse access to oracles OR and OH. Now, let me argue that if we want to estimate an entry of this thermal correlation matrix, then it's sufficient to estimate an entry of our polynomial approximation. And for that, we just have to, for that it is sufficient to learn the same matrix entry of all of the monomials in the polynomial approximation. And it is in fact this last thing that can be done can be done classically on a lattice model. And to see this, note that if we take the vector h to the k times j, then we know that this h to the k times j is only supported on a number of i's that scales like order k to the d. And for d is order 1, so for a d-dimensional lattice model, this number is still of polylog n size. So for beta as polylog n, we can estimate this thermal correlation matrix entry with a sufficiently small error. So indeed, the entry of m beta can be obtained classically with 1 over polylog n effort. And in fact, so this discussion was specifically about the thermal correlation matrix, but exactly the same thing can be said about the estimating entries of the Green's function using the same arguments and for the problem of time evolution. And I want to focus now specifically on the problem of time evolution to try and argue that even for the case of these lattice models, our approach can provide some speed up. So let's focus on the problem of time evolution in concrete settings. So our quantum algorithm has a runtime that scales like polylog n times t. And let's go to the time regime which we call the Lieb-Robinson time, which is the time it takes for the Lieb-Robinson cone to extend across the entire system. This might be an interesting parameter regime. So this is not the regime of the previous slide. And here we know that the best known classical algorithm takes time that scales like n times t. And now what is left to determine the speed up in concrete settings is to try and see what the Lieb-Robinson time will be for specific models. So for a d is order 1 dimensional lattice model, we know that the Lieb-Robinson time scales like n to the 1 over d because it's a d-dimensional lattice. And so if you fill in this TLR in these two runtimes, so the runtime of a quantum algorithm and the runtime of the classical algorithm, then we obtain a power d plus 1 polynomial speed up still. So this is quite significant for 3-dimensional lattice, for instance. This would be a quartic speed up. And for expander graphs, we know that the expander graphs have log size diameter. So the Lieb-Robinson time in that case is only log capital N. And so if we fill in this log of capital N into the two runtimes, we see that we retain an exponential speed up for these models. And of course, in general, as I've argued, the robust speed up can be proved through the BQP completeness of the problem. So to conclude, we give a quantum algorithm that solves several free fermion problems on n modes with polylog n effort. In general, we obtain an exponential speed up, and even in the case of lattice models, which are supposedly easy classically, we still obtain a polynomial speed up, which can be pretty significant in practice. Let me now note that our approach, at least of time dynamics, can be generalized in some ways, and one of the ways in principle in which it could be generalized is to free bosons. And finally, as an open question, it would be interesting to see if our algorithm can be useful when solving actual interacting fermion systems. Because as I've said at the beginning, free fermion problems, or the ability to solve these problems, is useful when trying to approximately solve interacting fermion problems. So an interesting direction of research might be to see if our methods can provably provide an advantage when solving interacting fermion problems. Right, so this was my talk, and I'll take some questions. Thank you.
Yeah, so thanks for the next talk. I got one quick question about the model you mentioned. Can you go back to the pages you talked about the free fermion model? Just let us take a look at what's the assumption we have.
The free fermion model?
Yes.
This you mean?
Maybe in the first few pages.
This or
Yeah, so I guess when we say we have this polylog in complexity, we actually assuming this HJK is sparse, right? That's the assumption, right?
that's right. Yep.
Okay, yeah,
Yep.
thanks.
Yeah.
I have a question, maybe a little bit on the application side, so sorry about that. But
No worries.
so I tend to think that applications of things you'd use a quantum computer for are probably most interesting at say more than 40 qubits, because otherwise you'd face pretty stiff competition from just a classical computer simulating the quantum algorithm in practice, even if it scales better, with constant factors and such. But if you are deploying this to a system with more than 40 qubits, you're needing more than 2 to the 40 fermion modes, which is quite a lot of non-interacting fermion modes. So the question is, do you kind of have a sense that there might exist systems that are sort of interesting to study in free fermion models that you could learn something about with 2 to the 50 modes, but not 2 to the 40 modes? Because you mentioned disordered systems as an example, but usually even in say semiconductor manufacturing or something, they talk about impurities and often parts per billion, maybe parts per trillion, but I've never heard of parts per 2 to the 50.
Yeah, so it completely depends on how quickly your system goes to the thermodynamic limit, right, as a function of system size. But I would say, at least in practice, so this is still smaller than the number that you mentioned, but I know that for people that perform quantum transport simulations, for instance, I think numbers like 10 to the 6 or 10 to the 7 are still interesting system sizes, and although it might be smaller than the 40 qubits that you were talking about, I think it's still in a regime where it could be interesting to try and use a quantum algorithm to solve these problems.
So you think there might be, you might be able to beat classical computers even at smaller sizes, even if you're only simulating 20 qubits or something?
Okay, we have no proof for this, but
Okay.
but might definitely be the case.
Okay.
Yeah. Good point. Yeah.
Yeah, you're saying you have a lot of ancillary qubits, so yeah, I have to account for that too. That's a fair point.
Indeed, the number of ancillary qubits scales with the system size quite like you will have maybe like 3n,
Okay.
Another thing is that I talked to some people who are doing like numerics on expander graphs, like they care about this, let's say, random, things that are actually, they have some moral connection to many-body localization. And there, like with expander graphs, you need to go to extreme system sizes.
Okay, thanks for the talk. So I hope to ask about this Lieb-Robinson part. So you mentioned that classical is ON. I think this is due to this exponential tail of the Hamiltonian out of the light cone, such that for classical algorithm you have to use this ON mode. But in principle, because I think actually this correlation out of the light cone is actually very small. It is actually exponentially suppressing when you are going, basically when your distance gets large. So I wonder, although this in the exact sense, you can see all the speed up, but if we relax the classical simulation algorithm by just also consider things within the light cone, do you still expect to get some advantage?
Sorry, you mean in the case where the light cone spans across the entire system? Is that or
because you mentioned that in this kind of time evolution you have to use time scale linearly with n and also t, and this is because you have to involve the whole Hamiltonian in your classical simulation. But actually, there's also a light cone in that notion. Although there is a very small correlation out of the light cone.
Mm-hmm.
So I'm wondering that if you do some classical approximation to kind of remedy it, you basically don't care much about what happened out of the light cone. You can also do a local simulation on a system size that early scale with your evolution time instead of the system size.
Okay, so I think I understand your question, but the thing is that this statement about our speed up in this particular time regime is about the regime where the Lieb-Robinson cone spans across the entire system, right? So if we go to smaller times, for instance, where the time is still polylog n, then we show that there's this classical algorithm that can solve the problem, and I don't think in that case we obtain a speed up.
Okay, thank you.
So I have a question about the assumption where you say small h is sparse. I guess you need some conditions on the basis that orbitals, right? So why that H is sparse? In chemistry, I can imagine you have to start from localized orthogonal bases. But then to get those, usually you start from non-localized atomic bases, which is Gaussians, which is actually usually non-orthogonal. And so then that will already assume you need to solve a n by n classical linear algebra problem on classical computers to get the orthogonalized localized orbitals. So I'm guessing, I'm just trying to understand, the assumptions here, why this is useful. So I wanted to hear some comments on that.
Okay, so why it's useful? I think it's specifically useful for, as I said, for instance, for lattice models or for expander
I guess,
graphs.
Maybe for chemistry, right? So you assume you have localized orthogonal orbitals to start from. That will give you sparse small h matrices.
But I think in chemistry, indeed, small h might be non-sparse. That's
it might be not sparse.
Exactly.
And then the query complexity argument might actually not valid.
I completely agree. Yeah.
Okay. Yeah. Thanks.
Yeah, maybe another quick question. I was just wondering, have you ever thought about making some comparison with the classical algorithm for simulating free fermion, or in context matter community, maybe people call it high binding model? Because I think when the sparse is very small, the classical computer maybe even, the complexity maybe even only depends on S.
I'm not sure it would only depend on S, but I think there's definitely a system size component in there, even if the sparsity is constant. But I think in general, even for sparse models, the classical effort would scale at least linearly with system size. If there's translational invariance, of course, then not. But
They showed an example of this BQP complete, so
yeah.
Maybe one more quick question if somebody has one.
When you say this can be generalized to bosons, can you explain how exactly that would differ from the Google paper?
Yeah, so it's
on
an
oscillators?
interesting question. So the main thing is that I think in terms of time evolution and determining global observables for a correlation matrix at some finite time, I think we either do as well as the Google paper or the Google paper does better. But I think in terms of estimating local quantities of interest, so correlations, single body correlations, or occupations of a mode, I think we have an advantage because we don't have the normalization factor that is there in the shadow state in the Google paper.
Thanks. Is that in your paper, the bosonic generalization?
We comment on it, but it's not fleshed out in full detail. Yeah.
That should conclude the session. So.
It's not